to look at a little bit later on if we want to. So let's start by describing the most elementary of storage circuits. This is called the SR latch. And what we'll do, and the book uses NOR gates, but you can do it with NOR gates or you can do it with NAND gates. And these are called cross-coupled NAND gates. And so we'll go in like this, and then we're going to go in like this, and we're going to call this S, and we're going to call this R. This will be the output Q, and this will be the output Q prime. And that is an SR latch. And that's it. And that's your first, most elementary storage element. Now, you don't want to assert both S and R at the same time. And the book goes into some detail, but suffice it to say, these things can start to oscillate. So S is not equal to R, is not equal to 1, or else you have what's called a race condition. Race condition. And so that's a bit of a problem. You don't want to have race conditions on these things. And what you do is you can write down the input S, R, and Q with all possible inputs and present states. 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and then you can write out your next state, and that's going to be grouped by 2, and this will be the hold state, this will be the reset state, this will be the set state. And we won't care what this is because you never want to assert S equal to R equal to 1. That gives us a race condition, and we don't know what the output will be, so we'll say we don't care about that either. It's forbidden. You're not allowed to do that with this setup. Now you can gate the inputs, you can use master-slave relationships, you can do all these other things, but if you have that, you don't assert both one set and reset at the same time. So then for the hold state, if you're in 0, your next state will be 0. If you're in state 1, your next state will be 1, because it's a hold state. You're not setting, you're not resetting, right? Hold state. Here, if in the reset, I'm going to group this over in here like this. In the reset, next state's going to be 0 no matter what. In the set state, next state will be 1 no matter what. And that gives us an opportunity now to take a look at what will happen if you want to invert this table using the so-called excitation table. Now the excitation table says, what do I need for S and R in order to make the transition from one Q state to another Q state? So what we'll do is we'll say if I want to go from Q to Q plus, all possible transitions, I should be able to write out what S and R need to be in order to make that happen. So if what you want to do is go from 0 to 0, then it seems to me like you can do that with S and R equal to 0, 0. And you can do it with S and R equal to 0, 1. You got your choices, which means we don't care what R is as long as S is equal to 0. And so we put in a don't care. Does everybody kind of see that? Who got confused by that one? It says 2 ways to approach changing from 0 to 0. And as a result, we didn't care about the reset. Intuitively, if you're in state 0, the hold state will keep you at state 0. If you're in state 0, the reset state will reset you to 0. So either way, it doesn't matter. You're in state 0, you're going to stay there, no matter what you do with reset. You can either assert reset to true, or you could leave it alone and you'll be in the hold state. That's fine. Similarly, if you're in state 1, which is here, and here, you want state 1 and you want to stay in state 1. That's here. Let's see, what else? Oh, and over here. These are the two places. So here you're, and let's get a color in here. Right? State 1 to 1, 1 to 1, and we can see now it's 0, 1 or 1, 0. Is that right? No, it's 0, 0 or 1, 0. 0, 0. And so now we have don't care 0, because it could be either a 0 or 1 for the set. And so don't care 0 plays an important role for us in the so-called remapped excitation table. And this is right out of the Cat's book, only I'm deriving it for you. And now we've got an alternative here. We want to go from, changing colors, from 0 to 1. To go from 0 to 1, I've got something here. This don't care I'm not allowed to use. So the only thing I've got available is a, looks like a set operation, and the input has to be 1, 0. Similarly, if I want a reset operation, I've got to go 0, 1. Now, let's take a look at how this is somewhat different from the JK flip-flop. We're going to group again by 2. That's the hold state. That's the reset state. That's the set state. This is the toggle state. And now we know if we're in the hold state, we keep Q plus so that it matches Q. So we copy Q. The reset state, we set everything to 0. The set state, we set everything to 1. Toggle state is different from SR, right? Because SR doesn't let you assert both 1s at the same time. You can't assert both S and R at the same time because it causes the race condition. But JK is different. JK is more reliable. It allows it. We allow for it. In fact, we design for it. And what it does is it turns into a toggle flip-flop. Toggle flip-flops toggle their present state from a 0 to a 1 and from a 1 to a 0. Does everybody kind of see that? That materially changes the excitation table now. Because now when we write JK, I need more colors. I like color. If I want to change from 0 to 0, there's 2 ways to do it. And it looks like it's going to be 0 don't care. Just like the SR flip-flop. And you could see, this is why I want SR, not RS. I want that symmetry. Similarly, if I want to go from 1 to 1, that's here and here. And there's 2 ways to do that. And it looks like I have a don't care 0, which is really just like the SR. You see the symmetry there? I mean, they're the same. What's the difference between JK and SR? And the answer is these 2 middle rows are different. And I'll show you why in a second. So now let's go and we'll say, let's assume I want to go from 0 to 1. So to go from 0 to 1, I see this, and I see this. And what that gives me is a 1 on J and a don't care on K. And you can see that's different from there. Now let's see what it takes to go from 1 to 0. Before we had 0 to 1. Now we're going to go from 1 to 0. Here's 1 to 0. Here's 1 to 0. And now we can see that J becomes the don't care and K becomes a 1. And again, you can see how that's different from SR. So SR is just like JK at the ends, but in the middle, the zeros become don't cares. This is why I feel it's so important to write SR next to JK in the order S and then R. I don't know why the book doesn't do it that way, but there it is. Can't defend it. That's what he did. He did what he did, and that's it. Now let's look at the toggle flip-flop. That's easy. Toggle flip-flop says if we're going to change, the input must be a 1. So there's no change here. There is a change there. There's a change there. And there's no change there. D flip-flop, also easy, even easier actually. If you want the D flip-flop to simply latch what's input, then if you want the next state to be 0, the input has to be 0. If you want the next state to be 1, input's 1. Just copy the next state over into the input, and then you're done. That is the remapped excitation table that I want you to use and that I use in my examples. I'm sorry the book doesn't do it this way. It's not my fault. It's not my fault. But there it is. Okay, now, who's confused? Anybody? So if you go to page 307 in CATS, what you'll see is that you can take Q plus, like over in here, and derive it as a function of SR and Q. Take Q plus over here, derive it as a function of JK and Q. Right? We can do some of these others as well. Let's see. We'll do T. Let's see. I guess we'll do it consistently. T and Q. Q plus will be 0, 1, 1, 0. Okay. And then that's the basic behavior of the toggle flip-flop. You can see what he did. If it's a 0 and he put in a 1, it changes to a 1. If it's a 1 and he puts in a 1, it changes to a 0, so it causes the toggle behavior. And we can group that. This is the hold state. This is the toggle state. Let's do the D flip-flop while we're at it. D and Q. Next state. And now, I think maybe you can see if D has got a 0 on input, the next state is going to be 0, 0, 1, and 1. Doesn't matter what Q is. It just latches whatever's used on input. So now I've got 4 different behavioral descriptions of 4 different kinds of flip-flops, and that's all the flip-flops I care about. That's it. So now what? Now I can write what is D equal to, and in this case D is, we could say Q plus is equal to D, right? That's my function. And based on the inputs, I can compare this against the inputs. It looks like Q equals D. So I write the characteristic equation for the flip-flop Q plus equals D. That's different for Q plus over here. Q plus equals, you tell me. Jason. Are you with me, Jason? What do you think Q plus is equal to based on this truth table? Can anybody help Jason? That's exactly right. T exclusive OR Q, which is also T Q prime or T prime Q. That's what it is. So you could see T prime Q is 0, 1, T Q prime is 1, 0. And that's it. That's the whole thing. Now, this one on JK, that's a little different, right? Because now we can do a K-map because we got a 3-variable truth table. There we go. So I got Q plus equals, so 1 over in here. There's a 1 over here on row 4. Is that row 4? 0, 1, 2, 3. Yep, that's row 4. There's a 1 on 5 and a 1 on 6 and a 0 on 7. 0, 2, and 3. 2 and 3, yeah, are all 0. 7 is a 0. So now I can loop. And that's going to be J Q prime. And I can loop again. And that's equal to JQ. It shouldn't be. 0, 1, 2, 3, 4, 5, 6, 7. Numbering K-maps. Let's make sure I've got this right. 0, 1, 0, 0, 1, 1, 0. Let's see, 1, 0. That's good. That's good. 0, 1, 0, 0, 1, 1, 6, 0. That's good. And loop from here to here. And you're going to get K prime Q. K prime Q. K prime Q. That's correct. So JQ prime or K prime Q. So that's my next characteristic equation. So I can summarize what I know so far. What do I know? D is Q plus equals D. For T, we have Q plus equal to TQ prime or T prime Q. For JK, Q plus is equal to JQ prime or K prime Q. And you can see the analogy here. It's very strong. And then for SR, well, we're going to need to do another K-map. 0, 1, 0, 0, 1, 1, XX. And now, do a loop, and I can write Q plus equals S, or, and now I got to do another loop, and that's going to be R prime Q. And that little guy gets written over here. Can you see that down there? Yeah, I gotta move it up. I gotta move the paper up, and then I gotta move it down. So now I've got Q plus equals S plus R prime Q. That is on page 307 of CATS. And so what I have done, even though CATS I think was a little too fast and loose with the derivation, CATS gives this to you, but his derivation doesn't use the SRJK analogy that I was trying to do, and I don't know, I kind of favor mine. Excuse me, I just have to, there. So from this, I think what we can do is see characteristic equations. We've got our remapped excitation tables, and now we're able, I think, to make practical application with some of our JK flip-flops and our SR flip-flops and our D flip-flops. So these are the only flip-flops equations we'll need. These are the only remapped excitation tables we need, and you've been able now to see exactly how to get these things. Are there any questions so far? No questions, really? No questions? Let's try a basic conversion exercise. What we're going to do is we're going to start out with a matrix, and this is not a matrix which you will find in the book. And what we're going to do is we're going to write on one side using, well, up here we'll write using, and over here we'll write implement. So we're going to implement, let's implement SR, JK, T, and D using SR, JK, T, and D. So these are all the flip-flops I know in the world. I can make a matrix. Let's make a matrix. And with this little matrix, I can see I can implement an SR using a JK, a T, or a D, but I would never want to implement an SR using an SR because that wouldn't make sense. I already have an SR. And I wouldn't want to implement a JK using a JK, and I wouldn't want to implement a T using a T, and I wouldn't want to implement a D using a D. So of the 16 elements, there are only 12 different ways to implement one flip-flop using any of the others. And I guess we can kind of see that. That sort of makes sense. So then comes the interesting thing. Suppose we start with the behavior of a D flip-flop. And we write all possible inputs and present states. We can then write out the next state. All right? D flip-flop, if the input is a 0, the output's a 0. If the input's a 1, the output's a 1. That's what D flip-flops do. But if we want the transition between Q and Q plus to be given here, then what you need to do in order to get a T flip-flop is put in 0, 1, 1, and then 0. Because if there's a transition, that causes a change, then that means there's a t used on input. Moreover, if you want t as a function of d and q, it's equal to d exclusive or q, or it's equal to d prime q or q prime d, however you like to formulate it, which means that I can implement a d flip-flop using a t flip-flop. And the way it looks is we take the t flip-flop, we run in an exclusive OR between d and q. That's an exclusive OR. And that's how you implement a t flip-flop. You implement a d flip-flop using a t flip-flop. Implement one using the other. And we can go right down the row. Right down the row. So now if I want to implement a d flip-flop using a jk flip-flop, just write down jk. But then the question is, how do I know the excitation table? Well, I have to copy it. I need that. I've already derived it once, but I don't want to have to keep rederiving it. So what I do is I write it down, d and t. D, I know if my next state is going to be 0, input must be 0. I know if my change is going to occur, then the input must be a 1. That's for toggle. But what about j and k? We did that already, right? That's going to be 0x, x0, and then 1x, and then x1. And what about S and R? Right, this is the excitation table. It matches JK, 0x, x0, and then instead of don't cares, he uses zeros. That makes it easy. So that's a nice way to go about doing this, because now when I go through and try and make a JK flip-flop in here, what I'll do is I'll say, okay, what gives me a 0-0 transition? And the answer is JK input 0x. What gives me a 1-1 transition? And the answer is x0. What gives me a 1-0 transition? And the answer is x1. And if I ask, well, what gives me a 0-1 transition? Well, the answer is 1x. And now it's pretty clear that I can make j equal to k, but how does it relate to d and q? Well, suppose I said j were equal to q prime. That wouldn't necessarily be good. Suppose I said it was equal to d. Well, that's all right. I could make j equal to d. And then k could be d prime. So if j equals d and k equals d prime, my goal is to implement a d flip-flop using a jk flip-flop. So I get my jk flip-flop, I run an inverter through, put in D, and that's that. And now I've implemented a D flip-flop using JK flip-flop. Similarly, I can go through and do an SR. Now my SR flip-flop, he's got to do the same exact kind of lookup I did before. I'm going from 0 to 0, so SR is going to be 0x. I go from 1 to 0x. I go from 1 to 1, so SR is going to be x0, just like the JK. You can see why it needs to be, sort of analogous. from 1 to 0, I see we have 0, 1. And from 0 to 1, I see the 1 to 0. Now it looks like S is equal to D, and R is equal to D prime. And now I can do the same exact thing with the SR flip-flop that I did with the JK flip-flop. And now what I have done is I have implemented a D flip-flop using an SR flip-flop. I implemented a D flip-flop using a JK flip-flop. And I implemented a D flip-flop using a T flip-flop. But I didn't implement a D flip-flop using a D flip-flop because that's silly. We wouldn't do that. Does everybody kind of see the approach that we're using here? Who got confused? So, Stephen Burns, you there? Stephen, what do I do if I want to implement a T flip-flop using a D flip-flop? I'm going to go to the next row. Oh, okay. So what we're doing now is we're doing flip-flop conversions. And what we did was we said if we want to implement a flip-flop, we have to get the behavior of this flip-flop, which we are attempting to implement, and somehow take that behavior and equate it to the flip-flops we plan to use. So if what you want to do is implement a T flip-flop using a D flip-flop, you must first define the T flip-flop behavior. So we write out T and Q, and then what do we write for Q plus? No. We have a T flip-flop. The input is 0. We're in present state is 0. What's the next state? Okay, it only toggles when the input is 1. So this is the hold state. This is the toggle state. There you go. That's exactly right. And now, if what you want is to see what D behavior will be, well, if you want D to be a 0, then the input should be 0. If you want it to be a 1, the input should be 1. Here it should be a 1. Here it should be a 0. And so D is equal to T exclusive OR Q. And so now, check it out. Here's the D flip-flop. And here's T exclusive OR Q. And guess what? It looks just like the implementation of a D flip-flop using a T flip-flop. You can use the same exact technique to convert from a D flip-flop to a T flip-flop. So you can go back and forth using the same exact thing. So that's cool, right? I mean, gee, how symmetric. How nice. Let's do another one. So we've done this cell. The next one is JK, which means we need to use a JK to implement a T. So if we put in the JK flip-flop right in through here, we need to know, how do I make 0 transition to 0? So I look that up over here and I write 0x. If I want to transition from 1 to 1, I write x0. If I want to transition from 0 to 1, I write 1x. And if I want to transition from 1 to 0, I write x1. And that's the whole thing. I mean, now I have to be able to figure out how to write j as a function of t and q. And I have to write k as a function of t and q. And it looks like j is equal to t, and maybe k can also be equal to t, right? Because, I mean, if t is equal to 1, 1 here, that's going to work. and the 0, 0 is there. That's going to work. So all I need to do is take my JK flip-flop, wire it together, and now I can implement a T flip-flop. Implement a T flip-flop using a JK flip-flop. And that's what we did here. Who's still confused by this? Am I making any sense yet? I hope so. Let's do another one. So next one up, we want to implement a T flip-flop using an SR flip-flop. SR. Okay. Well, now let's see. Who shall we call on? Daniel. Did I call on you already? Yeah. Yeah. Excellent. That's excellent. And so now it looks like S is kind of like the inverse of R. Maybe S could be equal to T and R could be equal to T as well. No, it doesn't look that. No, it's not right. What if R were equal to T and Q? If R was equal to T and Q, then S could be the inverse. So maybe that's a good way to do it. And that is a way to implement a T flip-flop from an SR flip-flop. And so if you think about it, you know, your SR flip-flop is really nothing more than cross-coupled NAND gates. Right? That's your SR flip-flop. So all I need is an extra AND gate for T and Q. Put that into the reset line, get an inverter, and now I've turned my SR latch into a toggle flip-flop. Isn't that cool? So you have essentially completed 2 rows of the conversion table. Sweet. So now that we've done, you know, the book is doing this all in about 6 paragraphs and leaves the rest as an exercise to the reader. I don't feel that's correct. You know, I'm going through all of this to kind of give you the, you know, numerous examples so that you can see you can implement any flip-flop using any other flip-flop. Let's consider for the moment this idea that we would like to implement JK flip-flops. Well, JK flip-flops are rather more complicated because the number of inputs is increased, right? It's J, K, and Q. So now we've got like a little 3-variable truth table here. And now when we look at Q+, we can group things by 2. This is hold, this is reset, this is set, and that's toggle. And now when we look at that sort of thing, we could say, well, hold, we just copy, reset, we set to 0, set, we set to 1, toggle, we invert. That's what they do. That's what JK flip-flops do. This is how they roll. The flip-flops roll? I guess they roll. I don't know. So let's implement right? A JK flip-flop using a D flip-flop. So that should be easy. Here comes D. If your next state is going to be 0, 1, then the input should be 0, 1, 0, 0, 1, 1, 1, 0. So everybody kind of see that? Or just, if you want the next state to be 0, 1, input has to be 0, 1. And so now, what I can do is I can, I don't know, write a K-map? Because what the hey? I can always do a K-map. But this time, I've got to do a 3-variable K-map JKQ 0, 0, 0, 1, 1, 1, 1, 0. Zero, 1, 0, 0, 1, 1, 1, 0. Now I got to loop it, and then I got to write it so that D equals, so now D is a function of J, K, and Q, so D is equal to J, Q prime, or, and now we can write K prime Q. That's cool. Because why? Well, because I implemented the JK flip-flop using a D flip-flop. And in fact, if I put it over here, here's my D flip-flop again. J, K, let's see, JQ prime, I'll put it into a little AND gate, K prime Q, put that into a little AND gate, and then run the whole thing into an OR gate and run that into the D key. And now I've implemented a JK flip-flop with a D flip-flop, and so I completed this cell right there. Now if I want to, I could implement the JK flip-flop using a T flip-flop. Right? And so we just write in what T flip-flops need to do in order to transition. So 0 to 0, inputs a 0, 1 to 1, inputs a 0, 0 to 0, inputs a 0. Sorry, this is 1 to 1, yeah. This doesn't change, that doesn't change. This doesn't change, that does change, that's why there's a 1. This changes, there's a 1. No change, there's a 0. There's going to be a change, that's a 1. There's going to be a change, that's a 1. Okay. Eddie, what do I do now? Oh, really? Well, I know T is a function of J, K, and Q. So I have a 3-variable truth table, J, K, and Q, and I see T as a function. How do I get the minimum sum of products form for the function T? Yeah, I'm going to make a K-map. Got to do a K-map. I mean, do I got it? Yeah, I got it. I don't know. Yeah, I probably should. So let's do a K-map again. Probably shouldn't be drawing it here because I may need the space. JK Q sloppy K-map. Yeah, That's it. That's all I want to do. So I got 0, 0, 0, 1, 1, 0, 1, 1. So I could loop over in here. I guess I could loop in over here. Probably got to loop over in here as well. So it looks like I need 3 product terms in all of this. And once I have them, I will have a minimum sum of products form in the form of T equals, and then over in here it's going to say something like, oh, I don't know, JQ prime. I don't know why I'm looping this 0. I don't need to do that. That's crazy. Don't do that. We'll just do this one. Yeah, don't loop the 0. I was looping because it says 1 over here. Silly me. So that's K, Q. And so now I have JQ prime or KQ. Let me just number this K-map. 0, 1, 2, 3, 4, 5, 6, and 7. So I should see 1s on 3, 4, 6, and 7. 3, 4, 6, and 7. So if you loop this, you're going to have K, Q. Yeah, that's right. KQ. So now if I wanted to go back, I want to find a JK using a T. So here comes the T. Here's J, Q prime, goes into an AND gate. KQ goes into an AND gate. The whole thing goes into an OR gate. This goes into a T. And that is how you implement a JK flip-flop using a toggle flip-flop. And so that gives me another checkbox. How am I doing here so far? You guys getting this? Who got confused? Be honest. Nobody's confused? Which part? Okay, so according to my little matrix, which is kind of like my outline for this lecture, I'm going right to left, bottom to top. So I'm sort of going backwards from the simplest to the more complicated. And what I did was I said I wanted to implement these using those. So this is part of the flip-flop conversion lecture, which the book kind of left out. And so what we did was I said if I want to implement a T flip-flop using a JK flip-flop, then I would need to somehow describe how JK flip-flops work, what it is I wanted from the T flip-flop, and then use a minimal form in order to express an equation for the T flip-flop input in terms of J and K. So if I wanted to do this again in terms of S and R, and this is why you don't write over here because you've got all this crap in the way, then you would have to proceed to take the 0 to 0 transition, which is here, and then write down SR0X. And you would see that here. And you might look for the 0 to 1 transition, and you write SR10. So you look for the 0 to 1 transition, and you write SR10, SR10. Then you want to look for the 1 to 0 transition, and you write SR01. So 1 to 0 transition, you write SR01, 1 to 0 transition, 01. And then you want to look for the 1 to 1 transition, and you write SRX0. So 1 to 1, you write X0. And here's 1 to 1, and you write X0. And that gives you the two different functions for S and R, and as a function of the three variables J, K, and Q. And so what that does is it gives you the ability to find the minimal sum of products form for S, and then the minimal sum of products form for R. And then having done that, you will have basically implemented a JK flip-flop using an SR. In other words, you will have done this. So then the next obvious step, if it's obvious, you need your K-maps. 2 K-maps, no waiting. And this is going to be JKQ and then you're going to want to have S equals and now I think the mistake I made before was I didn't use different colors. So we'll use a different color now. 0x00 0x00 1x10. And so here comes my loop, and that's equal to j q prime and now we need another K-map. We'll change colors. I think changing colors actually is really good. So now it's going to be x0, x1, x0, x1, x0, x1, 0, 0, 0, 1. And now I can do a loop, and I can write R equals, and it's R equals KQ. And now my implementation of JK using SR, that little square down in here, is J Q prime K Q. And so now we have implemented a JK flip-flop using an SR latch. So if you think about it, if the SR latch is just 2 cross-coupled NAND gates, I made a JK flip-flop using a couple of AND gates. And that's it. Done. And that's cool. And now I can implement SR latches using D, T, and JK. But I ran out of space on my little piece of paper here, so I'd have to start a new piece of paper. What do you think? I guess I better open the floor to questions here because I think I've covered a lot of material in a relatively short period of time. I'm going to start asking questions. Do you guys have any questions for me? No questions. Okay. Alvin. Are you with me, Alvin? Yeah, you. Alvin T. That's you. Yeah, I want to ask you a question. I would like to do this little section over in here. So that says that using a D flip-flop, I want to implement an SR latch. What do I do to do that? How do I do that? I want to implement an SR using a D. That's this little, I didn't do this yet. You need a little help starting? Yeah, so you can see what's happening here. When you wanted to implement a D flip-flop using anything else, you started by writing out D, Q, and Q+. So you needed the behavior of the flip-flop you wanted. So if you want to implement D, you have to write out what D flip-flops do. If you want to implement T, you got to write out what T flip-flops do. If you want to implement JK, you've got to write out what JK flip-flops do. So if you want an implementation for SR, what should you do? Yeah, there you go. So to do that, we'll grab a sheet of paper and we'll write out what SR flip-flops do. And we're going to group them in twos because this is the hold state, the reset state, the set state, and finally the forbidden state, don't cares. So what do I write over here, do you think? Yep, how about the reset state? How about the set state? There you go. You're doing it. So now we've got to write out the flip-flops that we're going to be using to do our implementation. So let's start off with the D flip-flop. What do we write out in here if we want the next state to be 0? There you go. You just copy the next state directly onto the input. And then if you wanted a T flip-flop, you want to use a T flip-flop to implement an SR flip-flop, what do I write over here? Yeah, we're gonna do them all because we're running out of time. So we're gonna write the excitation tables for the transitions. But if you just wanted to do a D flip-flop, we can go back to that. Let's do that. What do I do next? Sure, let's do that. I like a K-map. Because who doesn't like a K-map? So this is going to be S, R, and Q. And then it's going to be 0, 1, 0, 0. 1, 1, don't care, don't care. And guess what we could do is loop this and give it a name. Let's call it S. Yeah. The 1, 0 column. Let's see now. So it's 0, 1, 0, 1, 0, 0, 0, 0. 1, 1. Oh, I got it in the wrong place. I didn't number it properly. I did not number my truth table. Let's do that. 0, 1, 2, 3, 4, 5, 6, and 7. 6 and 7 should be don't cares. You are correct. You are correct. These should be 1s. Any other blemishes in my presentation here? My loop is still all right. It's still S. And then if I want this, I can go that way. And I guess if we would call that R prime Q. So that's all right. That worked out somehow. How did that happen? I don't know. So D is equal to S equals R prime Q. And how am I doing on time? Oh, we're out of time. So what we'll do is we'll just write out a D flip-flop, and then S, and then R prime and Q go into an AND gate, and then S and R go into an OR gate, and then that is how you implement a SR latch using a D flip-flop. And that gives us one more checkbox in our little matrix. I can't get to the other two because we're out of time. It's a beautiful day. Thank you for your attention. Good luck on the midterm. And, if you got any questions, bring them with you on Monday because you'll still have a little bit of time before the midterm. But please don't wait till the last minute to submit. Thanks a bunch. Thank you. Thank you.